Hello grade 12s, welcome to today's lesson. We are going to be looking at past paper questions on functions and inverses. This really lovely chapter that we're covering in our syllabus. So let's get stuck right in. All of the questions I've taken have come from previous exams. So this will be the standard and level of question you can expect to get. This first one is a pretty straightforward, easy one. So I thought we'd start off nice and simple and then we'd get into the more difficult stuff. All right, so it says, in the diagram below, the graph of f of x is equal to ax squared is drawn in the interval x is less than or equal to 0. All right, so I kind of just want to pause there quickly, and because I know some of you are seeing that inequality and going, what? So I'm kind of just going to take that away for now, and I'm going to draw that parabola as if it was all there. All right, so that would be the other arm of the parabola, and its inverse function would look like this. So when they add in this information, right, is drawn in the interval x is less than or equal to 0. So this is a restriction on the domain. They only want to look at that portion of the graph. So what happens is, if I restrict the domain of the parabola, right, so I only work with the x values in the negative x-axis, I only work with x values in the negative x-axis, then what happens is, when I erase that part of the parabola arm, so I then erase this portion of its inverse. All right, and then you are just left with these portions of each graph. Okay, so don't get intimidated by something like that. It's literally just saying your function has been restricted. I'm only looking in this area. I'm only looking along the negative x-axis from the origin. All right, so the graph of its inverse is drawn. We have a point P, and R is a point on the inverse. So first question, why, or is this a function? Is the inverse a function? And motivate your answer. So the reason why I did that whole story before, let's act as if the whole parabola is there, and let's act as if the entire inverse of the parabola is also there. Remember what happens now. To determine whether a graph is a function or not, we use the vertical line test. So you take a ruler and you draw a line down. And what happens is, if your ruler hits a graph more than once, as it would do here, right, then we would say that this is not a function. But because of that restriction, grade 12s, what it means is, well, because of that restriction, this portion of the arm has fallen away, and now you can quite clearly see that this vertical line does only cut the graph once. So therefore, it will be a function. So for question 1, you will say yes. Right, but we also need to give a reason for this. Okay, it does say motivate your answer. So the very simple thing to write would be that it passes the vertical line test. Right, that's what we were discussing a little bit earlier, right? That when I hold a ruler up to the graph, it only gets cut once by my ruler, so therefore it must be a function. Something that's a bit more mathematical, perhaps a little bit more accurate to say, but if you wrote this down, it would be correct, but you could say for each input, right, meaning for each x value, there is one unique output, right? So that would be, yeah, just again, it's saying the same thing, right? And this would be a one-to-one function. Hey, for each one x value, there's only one corresponding y value. All right, so that's something nice and straightforward. Let's have a look at question 2. If R is the reflection of P in the line y equals x, write down the coordinates of R. All right, so we know that our graphs here, the functions are reflecting over the line y is equal to x. And this transformation, if you reflect over the line, what happens is your x and y values switch. So if p on the original function on the parabola was -6, -12, therefore r will be, you literally just switch the coordinates around. So the coordinate of r will be -12, -6. Okay, it's really so simple. Just swap x and y around. I'm going to be saying that quite a lot of the time. Swap x and y around. Okay, let's have a look at question 3. So question 3 says calculate the value of a. So we were given y is equal to ax squared. You obviously want to sub in a point that's on the parabola. So we're going to sub in that point p, -6, -12. All right, so -12 will be a times -6 squared. That will become -12 divided by 36. All right, so therefore a will be equal to a -3rd. All right, and that looks really good. I want a to be negative because we can see that it's an arms down parabola. All right, so we are spot on there. Good job. Last one, question 4. Write down the equation of the inverse in the form y equals. Okay, so I always like to start off by writing the original function above it. So, whoops, it's not, we figured out, it was y is equal to a -3rd x squared. All right, that's the equation of my parabola. When you find the inverse, all right, switch x and y around. So x will be equal to a -3rd y squared. Now we need to make y the subject of the formula. So I want to get rid of this -3rd, obviously in front, and I also then will have to square root both sides. So I'm going to multiply both sides by -3. So we will get -3x is equal to y squared, right? And now to solve for y, we just square root both sides. So I know some of you are going to say, but I can't square root a negative. And I hear you. So first of all, when we square root, we must say plus or minus, and then we're going to say root -3x. All right, so first of all, I don't want you to worry about the fact that there is that negative there. Okay, we must work with what they've given us. So this is perfect. You're not going to be penalized. You are right. However, the plus or minus will be the problem here. If you look at our picture again, right, if you look at our sketch, if you were to say plus or minus, it would be dealing with the entirety of the graph, right? All of it. But remember here that we had the restriction, which chopped off one of the arms of the inverse graph. So we can't go plus or minus, because then that would be representing the entire function. All right. So we need to be careful now, because we need to decide, well, will it be plus -√3x or minus -√3x? Well, because it's positioned in the negative, that portion of the graph is in the negative y-axis, your answer will be -√3x, all right? So since y is less than or equal to 0. You don't have to add in that part, but that's why I chose the negative as opposed to positive. So if we were in the positive y-axis, we would have said plus √3x. Cool. Let's move on to our next question. All right, let's have a look at this question. It was out of last year's supplementary paper. A rabbit population grew exponentially, exponential graph, over a period of time. This exponential growth was modeled as follows. Y equals 558 times 1,08 to the power of x, where x represents the number of years and y the total population. Makes sense. Determine the approximate number of years it would take for the population to double. Okay, so, right, we've got y equals a times b to the x. That's your general equation of an exponential graph, right? So, in this case, we know that a is going to be 558. They're saying that they want the population to double. So where y is, I'm going to have double of 558, which is 1116, is equal to 558 times 1,08 to the power of x. Dividing both sides by 558, we get 2 is equal to 1,08 to the power of x. And you should realize here that we need to use logs in order to solve the number of years. So x will be equal to log your base 1,08, 2, and if we approximate this answer, we get that it will be approximately 9 years for the population to double, which seems like a long time. But anyway, especially because they're rabbits, you know. Let's look at B. So B says, determine the equation of the inverse. Okay, cool. So F, I like to start off with, y is equal to 558 times 1,08 to the power of x. So for the inverse, switch x and y around. So x is equal to 558 times 1,08 to the power of y. All right, so now we just need to switch into that log form. Therefore, y is going to be equal to, well, actually, before we switch into the log form, we need to get rid of this first, hey? So it will be x over 558. You want this base to be isolated, right? You want it to be alone. So now I can switch to logs. So therefore, y is going to be equal to log your base, 1,08, and then we have x over 558. All right, and that would be your final answer. Okay, isn't this stuff really easy? Let's have a look at the next one. All right, so this is out of another supplementary paper. If g of x is equal to x minus 6 over x minus 2. So by the way, this is actually a hyperbola. And I found this question because I want to show you how you can rewrite this into the format that you're used to seeing for hyperbola. So we're tackling some of our graph section here nicely. And h of x is 3 to the x minus 2. Well, we know that this is just an exponential graph. All right. Determine the inverse of h in the form y equals. Okay. So let's go for A. Right, we're looking at number 1 first. So for h, it's y equals 3 to the x minus 2. Remember that when we get to the inverse, step 1 is to swap x and y around. And then step 2 is to make y the subject of the formula. Okay, so you need to get rid of this negative 2 on the right-hand side. So you're going to add 2 to each side. So x plus 2 is equal to 3 to the y. And now we know we're going to jump into our log form. So y will equal log 3x plus 2. All right, and that would be the inverse. Right, next we need to sketch. Right, we need to sketch the inverse for question 2. Okay, so I like working with the original graph. Okay, so the original graph was 3 to the x minus 2. So what I like to do is just to find a point on this graph, because I know that when I then have to draw the inverse graph, I just take those coordinates from my original function and I swap x and y around. I prefer working with the exponential function then switching to the log graph, just because it's a function that we've been working with for so many years. So if I figure out the x-intercept here, so the x-intercept, we let y equal 0, so 3 to the x minus 2, so 2 equals 3 to the x, and now we don't have to worry because logs will save the day. We can figure out that the x-intercept will be at 0,63, right, if I round it off to 2 decimals. If I want to determine the y-intercept, right, what do? We let x equal 0. So 3 to the 0 minus 2, that will be 1 minus 2. So your y-intercept will be at -1. Okay, so why I've done that is, let's just draw. So I'm going to draw the original graph first. So let's just make a little Cartesian plane. Okay, so something like this. All right, so with the original function, you had an asymptote at -2, right? So I'm just drawing the exponential graph here, guys. I think it helps explain the inverse so much better if you've got the original function there as well. So we said that the x-intercept was at 0,63, so let's say about there. The y-intercept was at -1. So your exponential graph was looking like this. Okay, so that was y is equal to 3 to the x minus 2. Now when you have to draw the inverse, right, what do I keep saying? Switch x and y around. So if you had an asymptote y equals -2, switch x and y around. You're now going to have an asymptote at x equals -2. So underneath this, I'm going to draw your inverse function so we can compare the two. All right, so if y equals -2 was a asymptote on the original function, then x equals -2 will be the asymptote on your inverse. Switch x and y around. If the x-intercept was 0, sorry, not 0, if the x-intercept was 0,63, right? Now, switch that point around, your y-intercept will be at 0,63. So switch x and y around. Okay, then if your y-intercept was at -1, you will now get that your x-intercept is at -1. Switch x and y around. So in the end, this is what your graph will look like. So I'm just going to get rid of that for now. So now this is what your log graph will be. Like that. Perfect. Okay, so this was -1, 0, and this was 0, 0,63. Okay, so that would be the inverse function. And I mean, oh, this is so exciting. Just look at these two graphs. Okay, so there was the exponential. What did we do? We reflected about the line, y equals x. There's my inverse graph. Any coordinates that I had on the original graph, right? I literally just took the coordinates and switched them around because we switch x and y around when we're dealing with our inverses. Okay, so this is here, right? This is your answer for the second question. Okay, the other graph I just used so I could really help hit home like the concepts we're doing here. Literally switch x and y around. Okay, well, let's see what our third question is. Now that we're like all over the show. Okay, so we've sketched the graph. For which values of x is the inverse greater than 0? Okay, so let's go to our beautiful graph. There it is. For which values of x is the graph greater than 0? So for which values of x is it above the x-axis? That's what it's asking for. So we can see it's all of this portion over there, hey? All right, so our answer then would be if x is greater than -1. Okay, that was pretty easy. Right, so let's see. That was the second bit. So this was basically 2i, and there was 2ii. All right, question 3. So this question isn't really about inverses, but it's a really lovely question. So I want to do it. And I think we'll just use this space over here on the right. And just let me get rid of this other stuff. Okay, so let's see. We're going to take that g of x is equal to x minus 6 over x minus 2. Okay, so g of x is equal to x minus 6 over x minus 2. My goal here is to rewrite this as a over x minus p plus q. Remember that I want this because p and q will then be the coordinates for the point of intersection, right? Because that's how we determine our asymptotes in our function. So I need to get this to look like that. And the way we go about it is actually pretty simple. So we see in the denominator x minus 2. Repeat that in the numerator. All right? So it's x minus 2. The original question had it as x minus 6. So to get from minus 2 to minus 6, I must subtract 4. So the numerator still says x minus 6. Now we're going to split up that fraction. we're going to write this as g of x is equal to x minus 2 over x minus 2 minus 4 over x minus 2. Because now what happens? These two terms cancel each other out and just simplifies down to 1. Now, if I rewrite this into the format we are used to seeing, we can say, all right, so therefore g of x is a over x minus p plus q. All right, so now we're back to that format. Why did I need to do that? So that I could determine the equation of the asymptotes, so that I could figure out the points of intersection of the asymptotes. So the points of intersection for the asymptotes will be at 2, 1. All right, so now the question is to determine the new equation of h. So this graph is going to shift, right? So we just need to figure out what will the new function look like once this shift has happened. So what you're going to do is you're going to sub in 2 and 1 into x and y. So let's just write this out. It was 3 to the x minus 2. Okay, so this is what's going to change. So I'm going to rewrite this as y is equal to 3 to the x plus q, right? Its asymptote is going to shift. So let's sub in, just get rid of this. Let's sub in now. So 1 will be equal to 3 squared plus q. Solving for q, we get that q will be equal to negative 8. So y will be equal to 3 to the x minus 8. That will be your final answer for question 3. All right, so I think it was very valuable and useful for us to work through that. It's a beautiful question. All right, next one. Those coordinates. All right, in this question here, they've given us a arms down parabola without telling us the equation of the graph, but giving us its x-intercepts as well as its y-intercept. We also have an exponential function which passes through the origin and another point 1, 2. Okay, so we will be able to work out these equations quite easily, but let's see what they have in store for us. Use the graph to determine the value of x where f prime x times g of x is less than 0. What does this mean? So we know from our calculus that when I said f prime x, I was usually talking about the derivative. But remember that derivative also refers to the gradient. So in question A, we're going to be looking at two scenarios. We're going to be looking at where is the gradient positive and the exponential graph negative, right? So where is the gradient positive, but the exponential graph is below the x-axis? Or where is the gradient negative on the parabola and the exponential graph is above the x-axis? So when I'm talking about the gradient, right, when I'm saying f prime x, so let's look at where f prime x is positive. So this coordinate there, the turning point, right, your stationary point, we also know that this is where the axis of symmetry for your parabola is, right, x equals. So we need to determine out what that axis of symmetry is. Because before the axis of symmetry, right, this is where your gradient is positive. If you were to draw a line to the curve, right, we could see that before the axis of symmetry, that would be a positive gradient. And after the axis of symmetry, well, that would be where the gradient is negative. So I need to determine that axis of symmetry. So it's pretty easy because remember that the axis of symmetry is exactly halfway between your two x-intercepts. So we just need to find the average of those two values. So it's going to be negative 3 plus 1. All right, remember I'm getting negative 3 and 1 because they told me that those were the coordinates of the x-intercepts. We're going to divide it by 2. So your axis of symmetry will be at negative 2 over 2, which is going to be at negative 1. So for scenario 1, where the gradient is positive, but the exponential graph is below the x-axis. So we can see it's this area here, right? From x is less than minus 1. So therefore, when x is less than minus 1, or, so we've dealt with the first scenario, The second scenario is saying, where is the gradient negative, but the exponential graph is above the x-axis? So we can see that the exponential graph is above the x-axis after the origin, and in that area, right, we can see that here we have the negative gradient. So your second part of the answer will be when x is greater than 0. Cool, so I think that was actually quite an easy 4-mark question. Let's move on to B. So in B, we're going to determine the equation of this exponential function. All right, to find the asymptote, right, the value of q, I would start off here by subbing in the origin. Why? Because we know that anything to the power of 0 becomes 1. So you remove d as a variable. So we don't have to worry about doing like simultaneous equations and stuff like that. Right, we get that the value of q, the asymptote, is -1. Now, since we know the value of the asymptote, or the equation of the asymptote, we can say that y is equal to d to the x minus 1, and now we can sub in that other point, 1, 2. So 2 will be equal to d minus 1, so d will be equal to 3. Cool. So we found the value of q is -1 and d is 3. Awesome. Right, question C wants us to determine the inverse. Okay. So we'll bring the questions back up again. Now we're going to have to look. So for C, let's write down. So the original graph is 3 to the x minus 1. All right. So now for the inverse. All right. First thing we do is we switch x and y around. Now I want that base 3 to be alone on the right-hand side. So I add 1 to each side, and now I can jump into my log form. So y will equal to log 3x plus 1. That will be the equation of your inverse function. Cool. So easy, hey? All right, the next question is to state the domain of the inverse function. So let's think about the original function, right? The original function was 3 to the x minus 1. So if you had to write down the domain for this, the domain for the exponential graph is x is an element of real numbers, right? There's no restrictions for the graph looking left and right along the x-axis. We do, however, know that the range we have to consider that asymptote, right? So the range would be y is greater than minus 1. So why I put this down is because now when I look at the inverse, which is y is equal to log 3x plus 1, I'm literally just going to compare it to what I've done here above. Remember that we switch x and y around in this section. So if you had to do the domain for this, right, it's going to be that x is greater than minus 1. All right, remember that if I just do a little very rough sketch over here, okay? So this was your exponential graph, right? There was its asymptote at y equals minus 1. Now its inverse, we'll have the asymptote at x equals -1, and it will go like that, right? So we can see quite clearly there that the domain would be that x is greater than minus 1. Okay, let's have a look at the next one. All right, so in E says determine A, B, and C. All right, so we need to figure out the equation of the parabola. Okay, so I think to stop from scrolling back and forth all the time, I'm just going to come up to the top of the page again. All right, so to determine the equation of the parabola, very important skill that we must practice and know how to do. We have to look at what they've given us. So they gave us the X-intercepts. So we're going to use this. We're going to have y is equal to a, x minus x1, x minus x2. Remember that x1 and x2 is referring to the roots that you were given. So we're going to have y is equal to a, x minus minus 3. So that will become x plus 3, and x minus 1. Now we need to also determine the value of a, so I'm going to sub in the third point they gave us, which is the y-intercept. So 6 will be equal to a, 0 plus 3, 0 minus 1. So 6 will be equal to 3 times negative 1 times a will be negative 3a. So a will be equal to minus 2, which looks great because arms down parabola, I want a to be negative. All right, but that's not my final answer because I need to expand these brackets and then distribute the negative 2. So y will be equal to negative 2. That will be x squared minus x plus 3x, so plus 2x minus 3. So finally we're there. It's going to be negative 2x squared minus 4x plus 6. So therefore a is equal to negative 2, b is equal to negative 4, and c is equal to 6. And we were expecting c to equal 6 because we know that that is the y-intercept. Good. All right, so in the next question, they want us to sketch the graph. Okay, so let's just make some more space first. Alrighty, so I'm just going to make like, not a table, but I'm just going to do side by side, like a comparison of the two functions. So yes, this is for f. If we are over here, I'm going to look at f of x, right? The original function. If I look at the original function's x-intercepts, right? So the x-intercepts were negative 3, 0, and 1, 0. When you compare this now to the inverse function, so switch x and y around. So if the x-intercepts were negative 3, 0, 1, 0, these will now become the y-intercepts for your inverse function. So it's going to be at 0, negative 3, and 0, 1. If I look at the y-intercept on my original graph on the parabola, which was at 6, this now becomes the x-intercept on the inverse function, and we swap that coordinate around. The third thing we need to consider, the turning point. So we know it's at negative 1. I need to find the corresponding y value. I'm just going to look up here and do it. So negative 2, negative 1 squared, minus 4 times negative 1 plus 6. That will be 8. So if the turning point on the original graph is negative 1, 8, the turning point on your inverse function, switch those points around, will become 8, negative 1. Okay, so it's I just think this section is actually pretty easy and straightforward. Well, I just think if you lay things out this way, right, it actually makes it quite simple to tackle this stuff. Okay, so I just need to get a little Cartesian plane going here. Right, so quick x and y axis. All right, and we're just going to eyeball it. So we've got a turning point at 8, negative 1. Your y-intercept, your x-intercept turning point. Okay, so this was 8, negative 1, x-intercept at 6, y-intercept at 1, and negative 3. Okay, so there is your inverse function. Pretty cool, hey? And with this, could I call this graph a function? No, it's not a function. It doesn't pass the vertical line test. Next question. 0. All right, well done, guys. We are nearly done. Let's have a look at this last question, a really beautiful question integrating our calculus into the function and inverses chapter. Really beautiful. Here we've got the cubic graph where we don't know the full equation. It's negative x cubed plus mx squared plus nx plus p and the log graph. Right, it gives us coordinates to work with as well. Show that p equals 3, m equals 1, and n equals 5. So it is important that I work through this because the p equals to 3, well, we actually are going to use our log function to determine that. So for a, when we have y is equal to log 1 over px, all right? What we're going to do is we're going to sub in that point which they gave us. So negative 1 is equal to log 1 over p3. And now what I want to do is I want to rewrite this in exponential form. So the 1 over p will be your base, right? -1 will be exponent, and we'll then have that 3 on the right-hand side. So now if I rewrite this 1 over p, right, that will become p to the -1 to the power of -1 equals 3. So therefore, we just get that p is equal to 3. Amazing. So now we've got a bit more information from our cubic function. We have that f of x is equal to -x cubed plus mx squared plus nx plus, okay, 3. So we've got that now. We've removed at least a variable. So now we're solving for 2 unknown variables. We'll need to probably do some simultaneous equations here. All right, so the first thing I'm going to do, I'm going to sub in that point, -1, 0, as is. All right, so the first thing I'm going to do is sub -1, 0. So let's see what we get. All right, so it's going to be that 0 is equal to -1 cubed plus m times -1 squared plus n times -1 plus 3. So this all simplifies to, so that will become 1 plus 3, it will be 4. So this is -1 times negative, so that will be 1 plus the 3 from there is 4. And that will just become plus m minus n. All right, so there's a first equation that I've made. We can make a variable the subject of the formula. So let's say that n is equal to 4 plus m. Cool. The next thing we need to do, all right, remember that they gave us a stationary point, a turning point, and since they've given us that, we know that to determine the stationary point, we need to find the first derivative. So let's find the first derivative. So f prime x will be, let's have a look, it's going to be -3x squared plus 2mx plus n. All right, and into this, we're going to sub x equals -1, right, where the gradient is going to obviously be 0, because we know the gradient is 0 at the turning point. So 0 will be equal to -3 times -1 squared plus 2m -1 plus n. So if we simplify this, it becomes -3 minus 2m plus n, and I can make n the subject of the formula again. Amazing. 3 plus 2m is equal to n. All right, so now I've got my 2 equations, two really easy linear equations that we need to solve. So 3 plus 2m is equal to 4 plus m. So m will be equal to 1, and therefore n will be equal to, we just sub that back into either of the equations we made, n will be equal to 5. Right, and that's what they want us to prove. Amazing, isn't it the best? When you find that p is 3 and m is 1 and n is 5, and we are just like smiling and dancing. Easy 6 marks. Cool. Let's have a look then at our next question. Determine the interval where f of x and g of x are both concave up. All right. So what's really interesting here is that the logarithmic function, right, that function is actually always going to be concave up for all the x values in its domain, right? So g is going to be concave up for when x is greater than 0. So I need to then just look at the concavity for our cubic graph. So what's great here is that g of x is always concave up, right, in its domain, which is x is greater than 0. All right, so g of x is actually always concave up. It doesn't have a point of inflection where concavity will change. So what will happen is they will both be concave up then, right? They will both be concave up if the second derivative is greater than 0, right? We're just going to use our second derivative test here to figure out our concavity, and then to figure out where we want to find the x value at the point of inflection, right? And then we can determine where f of x is concave up, and then we can determine for where both graphs are concave up. So our second derivative, so the first derivative will be negative 3x squared plus 2x plus 5. The second derivative will be negative 6x plus 2. All right, so now for both will be concave up if the second derivative is greater than 0. So let's solve that now. So negative 6x plus 2 is greater than 0. Negative 6x is greater than negative 2. Therefore, when x is less than a third, it will be your solution. When x is less than a third, both our functions will be concave up. All right, cool. So now we can actually get onto the inverses bit. Write down the inverse of g in the form y equals. Okay, so we have at the moment y is equal to log third x, right? That's what our function is at the moment. So we know to get to the inverse, what do? We switch x and y around. So x is equal to log third y, and now we can jump into our exponential form. Y is equal to log a third x. Okay, so that would be the equation of your inverse. The next question wants us to determine the domain of the inverse. Remember that the domain of the inverse is the same as the range of the original function because we switch x and y around. So the range for this would be y is an element of real numbers, right? So the domain for your exponential graph will be x is an element of the real numbers. So that is a kind of theory that you should just know, right? That the domain of an exponential graph is x is an element of real numbers, its range is linked to its asymptote, and we switch that around when we get to its inverse graph. Okay, let's have a look at E. So E wants us to determine the x-intercepts, cool, and then hence solve for where f of x over g of x is less than or equal. Okay, so I'm sure you're seeing 7 marks and you're going, eek, but there's no need to eek. Let me show you why. All right, so we have y is equal to negative x cubed plus x squared plus 5x plus 3, right? We know that we have to let y equal 0 to solve the x-intercepts, and I'm also going to multiply through by a negative. So looking at your sketch, remember that if your stationary point is also an x-intercept, that you have that bracket which repeats. So we're going to have 2x plus 1 brackets, all right? And if you needed to now determine your third bracket, remember, you know that x equals negative 1 is a factor. We're doing a whole story about how to solve cubics. I'm not really going to go through that now. But x minus 3 would be your last bracket. Okay, so therefore our x-intercepts are going to be at negative 1 or x is equal to 3. If I wanted to determine the x-intercept of the log graph, all right, so this was for f, right? This is now for our g function. So we have y is equal to log 1 over 3x. We let y equal 0 to determine the x-intercept. We switch this into exponential form. So a third to the power of 0 equals x. So the x-intercept of the log graph is 1. Cool. So let's just fill in those values now on our sketch. So we've got negative 1, 1, and 3. So now we are dressed for success. Now we are ready to answer our question. Where is f of x over g of x less than or equal to 0? So we're looking at 2 scenarios now. Where is f positive or negative, but then you're comparing it to where g of x is negative or positive. All right, so those are your 2 different scenarios. Let's just highlight, let's look at scenario 1 first. So f is positive above the x-axis in this whole region, right? So basically when x is less than 3. we need to look at where the log graph is negative. So that is after its x-intercept. So if we now take this into consideration, so we can see it's just actually in scenario 1, this small area between 1 and 3, where the cubic graph is above the x-axis and the log graph is below. Be careful though with this including. We know that means we actually need to include the x-intercepts, but we also know that we don't want the denominator to be 0. So I'm not going to include the x-intercept of g, but I can include the x-intercept of f. So therefore, it's going to be when x lies from 1 to 3, but we don't include 1, since that will then make the denominator 0, which will then make everything become undefined. If we look at our second scenario, so where is f negative? So f is negative after 3, right? And the log graph is positive just in this small area here between 0 and 1. So when it comes actually to this scenario, there is nothing that works, right? So we just get the one solution from 1 up until and including 3. Okay, well done guys, we're on our very last question. Determine the values of k for which the root of the log graph is negative. All right, so I'm sure that you've realized something now as we've been exploring and working with logs, as we're looking at the asymptotes switching from the exponential to a log. You should have been picking up something that was happening. If you have y is equal to log a third x, right? That's what we have at the moment. Or what if I wrote it as x plus 0? Where is the asymptote for the log graph at the moment? Right, the asymptote, let me just get rid of all of this. The asymptote for the log graph at the moment is the y-axis. So the asymptote is the line x equals 0. What do you notice? All right, so what's happening actually here in the bracket is linking up to the asymptote for the log graph. So for example, if I had something like y equals log a third x plus 2, right? The asymptote here would be at x equals minus 2. All right, so what's happening in this portion is actually giving you information around the asymptote. So now I've just wanted to show you that because it then makes it makes answering this question actually pretty easy. So they are saying where would the x-intercept be, or what must k be so that your x-intercept becomes negative? So at the moment, the asymptote is at x equals 0. So obviously, it will be negative if we shift it to the left, right? And remember that when you shift left, you add. So if k is bigger than 1, if k is greater than 1, then your function is going to shift to the left. And if it shifts left, then obviously its x-intercept will become negative. All right, so you're going to take that log graph, the graph of g, and we're just going to push it to the left, which means that the asymptote will also shift to the left, which means the x-intercept will also shift. So that will basically happen since the asymptote is currently at 0. It's going to be for all values of k bigger than 1. All right, well done everybody. Good job.